just unmute yourself and interrupt me. I'm more than happy to respond there. And yeah, and that's, I guess, the very introductory things. So I've worked in various things about machine learning for code almost for a decade now, but the thing I wanted to discuss mostly today is this notion of code code completion, and I'm calling it pragmatic code completion because we can sense some of the cases where things work and some things don't work. There's other work I've done with some great colleagues. You can see their faces over here that I won't be talking today, but I'm more than happy to discuss them later if we have time. So let's start just talking about code completion. And specifically, you see here, I have Clippy here because it's one of the first kind of ideas that we have some form of assistance, right? So we go into the old days of 2019 or 2020. And at that time, we had a lot of, we have been thinking a lot about how to improve the experience with machine learning on IDEs such as Visual Studio and Visual Studio Code. And the most interesting thing there was that we knew that machine learning has had something to have to do with that. The idea is we wanted to combine this with static analysis, with information that we get, that we have within our IDE. So the goal there was to start with taking what the suggestions, what are the valid methods or functions or fields that a particular call site had, and we wanted to re-rank them to change the order in which things appeared. And we did this without transformers. That was early times, but also at the same time we found a way to make this very efficient. And we deployed this, in a way that it doesn't use a server that has GPUs. Everything runs locally. We can give really fast responses, quite accurate responses in predicting the next method. And that was a feature, and is a feature to the extent I know, that is used by Visual Studio and Visual Studio Code in quite a large set of languages. However, when we thought about the next step, the obvious next step is to do what currently you can see in GitHub Copilot, in Tab9, and in other code completion offerings. We thought that in many cases the completion itself is not actually the thing that is clear. Like if I were to drop any one of you into someone's ID and let you look at their screen, maybe scroll a bit the code at the top and below and try to say, what are they trying to do? The answer wouldn't have been clear. So in many cases, what this means is that we have some notion of uncertainty in code completion. The idea here is that the partial code that the user has written so far does not give us sufficient hints about what they want to do next, right? And we could ask the users to provide this extra hints, and in some cases this makes sense, such as in natural language. But in many cases, asking the users to provide these extra hints, this extra work of providing these hints, we synthesize the code for them. They look at the synthesized code, they check that it's correct. This whole loop, the cost of this loop isn't actually something that is worth their time. So it's not, and I think Eran Yahav from Technion was the first to coin this as a rule, that the effort that a synthesis job has to make should increase drastically the way that the effort that the users have to make. So in many cases, and I certainly do find this in my everyday coding life, the code completions, looking at the suggestion, trying to understand what is going to happen, and fixing it in the parts that is not going well, and then accepting a completion is much more tenuous than actually writing the code. So in maybe not introductory code, like things that you see in standard benchmarks like human eval or MPVP, in real life code where there is tons of dependencies, tons of internal code that you don't get to see very often, in those cases, code completion often fails. So the question that we tried to answer here was, how do we address this notion of uncertainty in code completion? How do we try to provide both useful completions in code, but also understand that there are things that are not clear and will have been clear to a human either. It's not just that the machine learning model is bad, but it's that we don't really have an idea about what to do next. And this is, I think, an example here, right? There we are about to predict something in line 6, but really, like, I can ask any one of you here to make suggestions about what should go in line 6, but there is not necessarily a single truth, right? You don't know what is actually what the user actually is intending to write. So the answer to that was that we thought that it's a good idea, instead of predicting concrete code, to predict sketches. So these are concrete elements of code, like the ones you see here. Pointer. The ones you see here. No, still not. Wait a second. Here, but we have introduced holes. Holes are places where you want to say, hey, this doesn't look right. This is a place where we don't know exactly what the content of this thing is, and that's fine. We will defer to the user and provide essentially a skeleton for the thing that the user wants to add in this particular location. So there are a bunch of examples where we pulled up from the way that Copilot used to work at that time. Copilot is an evolving service. We never know exactly what is happening, what stage, what model is being used, if it's updated. And you can see in this case that our model suggests this sketch here. So it has an empty and a hole at the location where you would get the flag name. We know it's probably a true, like a flag that will be either true or false. So, but nothing more. In contrast, Copilot suggested that probably version is is the right thing to do. And in practice, what happened is that the user actually wanted to say, well, we have the release, the pre-release, and the experimental thing. This was how the code actually looked like. So one way to combat this uncertainty of that was to introduce sketches. And while all of my talk about this topic will be about code, and to some extent the method is kind of tied to code. Yeah, I do strongly believe that these ideas are very interesting, and capturing these uncertainties are very interesting in standard large language models. You see a lot of examples on Twitter across various large language models that are offered from various companies about making, let's call them, stupid mistakes and be overestimating facts or saying things that are not truthful but seem realistic. So in these cases, maybe it would be interesting to find ways to say, this is the scaffold of the sentence that I want to reply with, but there are some parts, some bits and pieces that I don't know about. And saying I don't know is something that is human. Currently, large language models don't seem to be really good at saying I don't know. So this is kind of the ability that we wanted to add here. So Adam is saying that sometimes the suggestion changes the ground truth, like, oh, I didn't think of adding version, but that's a good idea. And that's certainly true. I think there is, especially in code completion, there is like, especially the ways that we evaluate it on an offline fashion don't necessarily match how users would actually use this thing. So there are cases where there are, let's say, 2 statements, or it could be 10 statements, where the order of those statements doesn't matter. And you would first write statement A, but the model would first write statement B, because there's no data dependency between them. You could do either. And in those cases, that's certainly something where you can say, the model made a good suggestion. But there are also cases, I think, where I find this very often with the suggestion code completions for large language models, is that they don't know the type of an object, so they suggest a method that doesn't exist for that object. And sometimes I trick myself into believing that this is probably the name of the method that I should call, until later, when Python, for example, tells me, hey, this is not actually a method of the thing you're trying to call. So there is certainly both of those things, right? So there are things where the language model and the completion edging actually gives you more information, or at least give you something, a different way of doing things that is right, at least with your definition of right or your intent. But there are cases where the model just makes mistakes. I think there is another example here, again, from comparing our model, which we'll call GRAMMFORMER, and the standard code completion model. And here, what you can see is that the model is not clear about what it should do in line 11, and that's fine. But in some sense, there is a good chance within this context that you're going to read the second argument from the command line, but the name of the variable that you will place things, so here, is not obvious. And GRAMMFORMERS can capture this uncertainty and tell you, hey, you probably want to read the second argument of the command line, but from this context, I wouldn't know what is your intent. Whereas essentially left to right code completion, like the codex here, has to make some decision about what comes first in order to suggest a full line. In this case, the model of the codex did suggest something that didn't make sense. Now, you can argue that the suggestion in line 11 is innocuous. You can start typing and it will eventually give you the right answer, which is certainly one possibility. But there are cases where suggestions like this should give some extra value, should let you fill in the things that are obvious, complete, and then the user comes in and gets to write the code that should go in the holes. So with that, I guess, the ground truth here in this case, because this is some code that we found on GitHub, was that the developer wanted to store this in a variable called ID. So this is the high-level intent of what we set out to do, and the question now is how. And we were inspired by some models that were pre-transformer that looked at the grammar, hence the name of the code, hence the name of our transformer, which is GRAMMFORMER. The idea is that you can take a view of some code and set it as a set of terminals, terminal symbols like R and equals, and a set of non-terminal expressions, non-terminal symbols like expression here. Then you can ask a model to pick some non-terminal, in this case there is exactly one, and predict a way to expand this non-terminal by one step. And once you expand the non-terminal, like in a context-free grammar or in most formal grammars, you replace the non-terminal with the expansion, and you can keep going by asking a model, hey, which non-terminal should I expand? The model says, this non-terminal, how should I expand it? This is how you should expand it. Okay, we've expanded this, and so on and so forth. So we can keep playing this game again and again, but the idea is that you have an expression which has terminals and non-terminals, and you have to pick some non-terminal, any non-terminal, and you have to predict an expansion, which follows, of course, the programming language grammar. And I think my animation keeps going for a while, which doesn't make a lot of sense. But you can think of this as a way of producing some form of generating code, not left to right, token by token, but by following the grammar. And once you have this expression here, where you have the non-terminals, you can take the non-terminals and you can essentially convert them into wholes. And now you have a sketch that is predicted. Not a particularly useful one for this example, but hopefully this gives you the high-level idea of how things would work. Now, this is the high-level view of how GRAMMFORMERS would work. Now, the question is, how do we actually achieve that? And it should be clear that transformers work, right? I think that's clear to the machine learning community for a while. So the question is, can we get some way to get the transformers to follow this particular way of generating code? And it is to use an encoder-decoder model, or at least a model that resembles an encoder-decoder model. And the first thing is to encode the partial code that we have. So the code with the terminals and non-terminals, encode it, and use this encoded representations. So it's an encoder transformer. Use those representations to select one non-terminal symbol. So in this case, this selector model can also say, hey, I want to stop, right? I don't want to continue to expand either this non-terminal here, this expression 1 or expression 2. The 1 and 2 are just for visualization purposes. I say this is all the confidence I have about completing the code, and that's the answer that you want to have. So if the selector model says stop, then we stop, and we have essentially a sketch that is as good as at least the model believes it can get. But if this is not the case, right, then we can take this decision that was made, and it's important to say this is a discrete decision, right? We have to select either this or this, or this non-terminal. We cannot select both in this case, or 50% one of them, or 60% one of them, 40% another one. So we have to make a discrete decision. Say we're going to be expanding this symbol here, and then we can ask the decoder, as in an infilling model, how do you take this non-terminal symbol and actually expand it, right? So in that sense, we query our model, our decoder model, to say that given this input and the fact that we're looking to expand this non-terminal, how would you expand it? And the model will give you an answer. It might be right, it might be wrong. That's something not that we'll hopefully train it to be right. And what we'll do is we're going to take the expansion that was predicted here and replace it with the non-terminal here. So this expansion may and will all commonly have other non-terminals that we will also have to be able to expand in subsequent steps. So this now becomes slightly more concrete, and in the way that we get this model to work, right? If we magically had an encoder and decoder and the selector model trained, well, this could be the exact way that we wanted to synthesize sketches. And we'll see ablations later with much simpler models that try to produce wholes or things like that are standard left-right models. So you can generate a sketch from left to right by producing token by token, but one of those tokens could be a whole. And as we'll see, this won't work as well. And we can discuss this. I think it's an interesting question of why this is the case. But let's pause for that. And now the question that we need to answer is, we have this model, how are we going to train this? And again, there is going to be two steps here. And it's not the only way of doing this, but I think this is a reasonable way of doing this. At the first step, we know that we cannot do standard training of like standard supervised training of PS, because there is a discrete decision involved. So eventually some form of reinforcement learning might be necessary to have. Now, what we do is we take a first step, which is more or less a pre-training step. And the idea is that we pre-train a model by taking learning the weights of the encoder and the weights of the decoder, but making random decisions about which non-terminal to expand. We take probably a few of them and say that given this partial code here, this code with terminals and non-terminals, try to expand expression 1 and expression 2. And once we have pinpointed the decoder, hey, can you fill in this particular thing or this particular non-terminal? We give exact supervision about how to expand this. So we do that by following the programming language, grammar, and a corpus of code that has essentially the concrete expansion for those non-terminals. So this is a good step, right? This is a good step towards getting an encoder and decoder in the plausible space. And the question now becomes what's next, right? How can we train a model that is this that makes this discrete choice, this PS, the selector model. And the idea here now is we have to do something that is more has to go through this discrete decision, and this will have a flavor of linear reinforcement learning. And specifically, we opted for something called self-critical policy gradient. But the high level, the idea is that we have some reward. We'll discuss the reward. There are many possible things that we could use as rewards, and we want to take the decision that gives us that improves on our reward, whether this is to expand a particular symbol or whether this is to say stop and let's not expand. So with that, I've described at least at a reasonably high level a training process that goes from the pre-training, which gets us a reasonably informative encoder and decoder, and which we can scale up and can do fairly efficiently, and a fine-tuning, if you wish, or the actual training that uses some form of reinforcement learning. So this discrete decision here in order to tune both the encoder, the decoder, and the selector. What I haven't mentioned is the reward, right? We have this reward here that tells us how good or bad a particular sketch is. So the way to measure this, I think, is still roughly an open question. I'm not saying that this is the answer that we have giving next is the best one. So we want obviously a sketch to be accurate, right? We don't want to make suggestions that are going to be incorrect, things that will cause the user to either reject the particular suggestion, or or in some way to go back and have to accept the suggestion, go back, make an edit, and so on, which is still a valid thing, and sometimes it works. But if we can avoid this going back and editing, that would be great. So here you can see essentially cases where something is wrong. So we don't want to make these suggestions. At the same time, we want the sketches to be as specific as possible, right? I can always make a suggestion like the one you see here, although that's probably not useful for anyone, right? Whereas this suggestion here on the top, that's probably much more useful. It contains much more information. So obviously there is a trade-off between those two things, right? It's not that In order to get as accurate as possible, we can always suggest something that is very vague, but that's not going to be useful. And instead, we want to try to suggest something that is specific. So we need to find a trade-off, and the particular trade-off that we used during our work, which can arguably be changed to other things, is to say that, well, first of all, that you can imagine this sketch be like to transform it to a regular expression, to say that in the whole anything can go. Does this sketch essentially match our ground truth? And this is the second term here, and this is 1 if it does, or 0 otherwise. So this is a very strict metric. And then we have this fraction here, which says what percent of the tokens of the terminals have we actually managed to predict. So so if we predict like something that is very abstract, this will be very low. If we predict almost the full thing, this will be very close to 1. And you can see here how this what we call regular expression accuracy kind of works for different suggestions for this particular ground truth truth sentence here, that the one I'm pointing here. Now, one thing you can see, and I think one thing that is slightly problematic with this, is that this is a very harsh measure. So this is something that that the time you make a single mistake, the regex accuracy falls to 0, and that's not good, right? Or at least it's not help the model learn, and we want to make the learning slightly less steep. So in practice, what we're going to use as a reward is the average of the regular expression accuracy, the thing I just described, and the standard ROUGE score that has been used in summarization, in natural language summarization, which gives kind of smooths out the idea that small mistakes are okay. They give us some improvement, but regular expression accuracy will still be here in some way to provide this extra information about the trade-off and to nudge to avoid making mistakes. Okay, so what I've done so far is I said we want to tackle uncertainty. I think that's something that is very common, very important across all things in transformers, not just in code, but also in natural language. I've also said that in code, this is important because we want to avoid, for example, introducing bugs. And one's particular way of doing this is with grammar, because in grammar, with code, we can almost always parse deterministically the code that we have. So that's unique. We cannot have that in natural language, at least in the most common scenarios. And then, given that, we've said that, okay, now we want to follow a grammar, we want to create sketches. Let's try to do this with an encoder-decoder framework of transformers, or it could be without transformers if you wish. And let's try to optimize this particular reward. So how does this compare with other things? So first of all, we train an equal sized in terms of parameters, traditional encoder-decoder model. So a model that encodes the prefix and decodes the suffix in some form or another. We can also train a model that keeps decoding in a causal way, in an autoregressive way from left to right, but has an extra special stop token that is trained again with some form of reinforcement learning to say this is where I want to stop. I want to stop. I don't have sufficient confidence to predict what is coming up next. Then we have a standard causal language model that is essentially a decoder-only model, if you wish, that we've also introduced this extra symbol of whole, and we are training this again. We are pre-training this to introduce the symbol whole, and then we're fine-tuning it with reinforcement learning in a similar way in order for it to learn to add this special whole symbol. And then we have our model. I'll get to Frau's question in a second, but what you can see here is that Generally speaking, our model is more achieves better score in the regex accuracy, assuming you believe this metric, of course. I cannot do something if you don't. And it also gives you certainly larger suggestions. And I think this is a really important thing, because it says that most of these models, because they generate in a causal way from left to right, they generate the code, at least in the Western way that the things are called from left to right. They feel less confident about suggesting things that are correct, and hence, especially these two models, like stop suggesting early. And whereas GRAMMFORMERS, because they can insert a hole easily and predict the things that come after the hole without a lot of problem, they do get longer suggestions. I want to stress that the way that regex accuracy works is a bit odd and maybe unintuitive. And the idea here is that a 47% regex accuracy doesn't mean that we have an exact match of 47%. It could be that which is not, these are extremes. This is, neither of them is actually true, but we get all of the sketches correct, but we only specify 47% of our tokens, or maybe we get 50% of correct and 94% of them have the tokens specified. So in that sense, it's a 47% is not necessarily as bad as it would be if we wanted to do exact match. Okay, so I'll pause now and go to the questions in the chat. Feel free to unmute yourself and ask more questions. I have a few more content later, but we don't need to go through this. So Franz is asking if there is a specific reason to use ROUGE with regex accuracy, or other metrics such as CodeBlue can also work. And I would say that they would certainly work. So I think this is the slide we were discussing. I think at the time we were working on this work, CodeBlue wasn't a thing yet, hasn't been published. It would arguably be better. I know that Uri Alon, who's also in the call, has CodeBird score as a way to get the semantic equivalence of two snippets of code, a suggestion and a ground truth. That could also be a great alternative. The extent that the reinforcement learning works, this is reward shaping. You can change the reward in whichever way makes sense. And I think this is maybe this is touching to a very interesting and important yet problematic issue. We don't really have models of the users, right? We don't know which suggestions the users find actually useful or not. You can measure the suggestions that they accept, but this is not going to be actually true, because maybe it's muscle memory, they pressed tab by mistake, or maybe they went back and edited things because they like doing that, or maybe others find that a small mistake somewhere is very annoying and they are not going to accept this. So finding models that match the perception of the users, the perception of the utility that the code completion thing has for users is important. And arguably, that's also going to differ across users. Maybe an expert developer has a very different utility function from a beginner, or maybe two expert developers have very different tastes on how they want things to get done. So I think finding the correct rewards for code completion is a huge problem. It's an open problem. I don't think there has been made sufficient progress in there, and I think it's worth looking further. I'll move to the next question, unless there's someone interrupting me. So Zhang is asking, when you were preparing label data, how did you decide a good hole, i.e. an uncertain hole? So we don't decide on where to place the holes ourselves. So let me try to pull this slide here. So the model has this selector model here that essentially has to decide when to stop this recursive expansion of expressions with non-terminals, expand more and more non-terminals, and so on. Obviously, if there are no non-terminals in the expansion that you have, then you cannot do anything, you're done. But in the cases where you have non-terminals, like here, the selection model has to make a decision whether to expand or not, whether to predict this special stop symbol here, or whether to pick which non-terminal to pick to expand. So during training, the reinforcement learning part, we don't tell the model where to place a hole or not. That's completely learned by the reward function. The reward function hopefully tries to like nudges the model to say that when you're uncertain, don't expand this because you're going to make a mistake, and you'll get essentially a negative reward. The regex accuracy of the thing you generate is going to fall to 0. So, so in that sense, I think that let me actually find this slide here. So in that sense, this will get a very negative, like a decision that gives you the wrong answer. Will give you like a bad reward, and therefore the model will try to avoid doing that. Yeah, so I hope this answers that question. Feel free to elaborate or unmute yourself. I'll continue the Gab's question. For lines that have multiple holes, how do you represent the other holes while expanding one of them? Okay, that's a great question, because I think this was not entirely clear. So let me pull up, I guess I'll pull up this slide here. So what you see here is this particular expression, this particular line has R equals some non-terminal expression times open parenthesis, non-terminal parenthesis, non-terminal close parenthesis. So the way we do that is that like transformers necessarily need sequences of characters, right? So we don't have any other way of passing that information. We almost don't have another way. So what we do is we have a special way of representing non-terminals, and like terminal symbols are represented as you would imagine them in most large language models. But non-terminals have a special way of representing them with special special characters. I'm using these braces here in such a way that we tell to the model this is a non-terminal. So essentially, when our model, again, I need to change this to here. So when our model, when the encoder takes in as an input, it is still a string of characters, but some of those characters have a special delimiters that say this is a non-terminal, and this thing here is also non-terminal. So so the model kind of knows, or at least learns, that these things are non-terminals. These are the things that I can expand, but this is also part of the data. Does this make sense? Or
yes, thanks.
Yeah, cool. So Arias is asking whether we lose exact match accuracy by using holes, and yes, which brings us to the next slide I didn't manage to get at, which I think is this one. No, I think it is yeah. These two slides are for the caption is missing, for different programming languages, so it doesn't matter. But what you can see is that that the length of the thing we are suggesting is bigger as we improve over like as the ground truth is also longer, but at the same time, for different diagram, and I don't think I have it. But in any case, I think I'll respond. Ignore this diagram. You're certainly right. The model does sometimes become over conservative, if you want. Is more conservative in completing in adding holes and not expanding them, and in that sense we lose exact match, right? So and the reason we think this is the case is that that regex accuracy is a very strict metric. So so imagine that you hadn't predicted this store false here, and you insert a hole, then your regex accuracy would actually be 0.8, the thing you see here. But the moment you make a small mistake like this one, maybe it's not a small mistake, that's something to be discussed, then regex accuracy falls to 0. So because the model gets this huge penalty, but due to the training, it becomes more conservative and introduces and does not expand in some cases holes that maybe you as a human or me as a human would say this is obvious and should be placed here. So I think this is probably an artifact of reward shaping, but like and the way that we used we defined our reward, but it's certainly an issue. On the other hand, we are also losing, like in some cases, like we are gaining something by not predicting incorrect code that wasn't intended to be placed in there. And I would argue this is much more important in the sense that like maybe the user finds this, right? When she accepts the completion, she looks at the code and sees directly that this place here is wrong. But what would happen in the cases where the error is more subtle, right? When you start now introducing a bug, the bug goes unnoticed, you commit it, you test it, it doesn't, like your tests don't catch it, then it moves to production, and then you find a bug that you introduced, that the code completion tool introduced. Maybe that's a bigger problem. Maybe that's what's already happening if the user is typing things, so maybe that's not a problem. But again, there is something gained and something lost in this case. Okay. So I think, let me see. Yeah, so I think with that, I've mostly discussed the work that we've done with Dayagu and Alexis Witkowski on sketch completion. I think it's a very interesting problem of how to capture things. I think there are many important questions, like how to this model has more computational cost than a standard transformer. That's a problem, right? The user experience, the way that you develop things in the IDE in order to support this, that's also very different. But more broadly, I think we need better ways to represent uncertainty. And I think this is a very interesting research question. So with that, again, I'll pause to continue the discussion, and I think I have one more slide, which we can also skip if there's no time. So I'd like to know, what do you think? Models that generate terminals directly versus models that expand on terminals. I guess the models that expand on terminals need to generate much more tokens, which might make the task harder. And the existing LM is able to generate grammar correct in most of the cases. So let me see. The results that we have, and I think that's without discussing the computational cost, right? Because I think that's still an important part of the equation, suggests that while grammformers do indeed make many more steps, they are still getting bigger, longer suggestions, right? They still get them more right than traditional models. Obviously, all of these things are on relatively small models, right? If we were to expand this to a huge model like Palm or ChatGPT or GPT-3, GPT-3.5, and so on, maybe things would change. And certainly the computational cost would be enormous. But at least at this scale, we can say that the many more steps doesn't hurt the performance, which I think it hurts the performance as in accuracy, right? It definitely hurts the performance as in the computation. We need much more computation compared to a standard left-right model. I think your question also touches on the question is, why is this model, this language model that can also introduce holes, why is this worse than our model? And obviously, I don't have an exact answer. I have a few hypotheses here. And the idea is that you have a model generating from left to right. And let's take an example where you're calling a function, you don't know what's the argument, the first argument that you want to have, but you're certain about the second and third arguments. Or maybe you're certain about the second, not entirely, but certain about the third. Now, the left-to-right, the causal language model will just start generating, open the parentheses to make the invocate, to start adding the arguments, and will introduce the whole. Now, at this point, the model has to learn how big of a step it has to make. What is the whole going to capture? Is it going to capture just the first argument? Is it going to capture the first and the second argument? Is it going to capture a portion of the first argument, and so on? And this seems to be a hard problem. This seems to be something where there is no clear answer. So when the model is asked to decide what should come after the whole, after this special symbol, usually the models, at least the models we've trained, we've seen them being confused about what does this whole should represent. Maybe there is a better way to train these models and they can overcome through this problem. Maybe if we went for larger models, then as we know, this larger model have emergent behaviors, maybe adding these holes wouldn't be a problem. But at least in my mind, like this left-right thing has much more uncertainty to capture, and it's likely very unclear how to achieve this. It could still be able to represent things in a grammatically correct way, that's for sure. But this notion of a decision about what to include in a whole, where to stop, where to start, this seems to be very confusing in the way that essentially autoregressive models factorize the probability that they have. Okay, I think Danny Dig has the next question, and we're almost out of time, maybe. I'm wondering, what is the runtime space consumption? How do you envision Grammformer being used in live coding sessions in the IDE? Okay, so how is this works in practice? I've left Microsoft since we wrote the paper, so the effort to use or not use has probably gone on without me, and maybe they have reached some form of understanding. The runtime and space consumption is not enormous, in the sense that we do get an extra runtime, like an extra latency in suggestions, but we've seen a dramatic decrease in the way that these models are served in the recent past. Obviously, as models like GitHub Copilot or Tab9, they need to have a client-server architecture. You need servers with GPUs, with TPUs that are able to make these computations one-off. And this is a departure from what was happening before. So in that sense, the runtime and space consumptions are very similar to those that are in these existing models that have been deployed, like Tab9 and Copilot, and maybe other ones that I'm not mentioning. But generally, I wouldn't be entirely worried. The UX experience, though, I think that's a big problem. That's a big question. There is a question of whether we need to educate users in order to get them to use this feature efficiently. Maybe it is more disruptive. Maybe there is some form of some different way of interacting with the ID in order to present sketches. I think this is a big open question, and I'm less certain about it now than I was before starting to work on this work. So certainly a lot of interesting research questions, especially for HCI people and software engineering people in the audience here. So finally, Adam is asking, what about hybrid models that can optionally fill in holes hierarchically and indicate confidence? Yes, sure. I think there is. I don't believe that the way that we're doing Grammformers is the end game, right? That's the final model that everyone will have, right? I think we know that in infilling tasks in code like UL2 and other things work really well, and T5 work really well. So find better ways to accommodate these ideas of having holes with these models to get both performance in terms of computational speed, but also in terms of accuracy or suggestion utility, I guess would be the right term, which is an unknown in some form, is certainly great. And things again to indicate confidence. I think that's a huge deal in machine learning, right? I think there is even before deep learning, even before transformers, maybe not before deep learning, but before transformers, we know that these models are not really well calibrated in some form or another. We know that that there is more to be done to understand how these models are confident or not confident, and so on. Yeah. Okay. I think we're out of time, so I think I'll just stop here. And yeah.